So basically, what we have covered in the previous lecture, we have already looked into the part of the introduction as well as the performance parameters of jet engine. So for today, we are going to look into the aspect of turbojet, and hopefully in lecture number 11, we will look into the next aspect of the chapter, which is the turbofan. With regards to the topic on turbojet, we will now look into the overview, followed by milestone of turbojet engines, and then we will cover the aspect of the thermodynamic cycle analysis of a single spool, as well as the performance parameters of a single spool and important definitions, right? With regard to the overview, of course, you have already heard the term turbojet, turbofan, turboprop, and also prop fan engine, and it is a family of the gas turbine engine. Okay, so the three successive modules in a turbojet comprises of the compressor. Okay, when air going into the compressor being compressed, and pressure build up, and before the flow goes into the combustion chamber, and then finally goes into the turbine, constitute what is called the gas generator. So the air is squeezed in the compressor to many times its normal atmospheric pressure, and then forced into the combustion chamber, where fuel is sprayed into the compressed air, ignited, and burned continuously in the combustion chamber. So basically, that is the basic principle of the turbojet engine, right? So what happened inside the combustion chamber? Basically, this raises the temperature of the fluid mixture to about 600 to 800 degrees Celsius. Okay, this is an early turbojet engine, and the resulting burning gases expand rapidly rearward and pass through the turbine, which is connected to the compressor via a shaft, and the turbine extract energy from the expanding gases to drive the compressor. Okay, so if the turbine and the compressor are efficient, and what will happen is that the pressure at the turbine discharge will be nearly twice the atmospheric pressure, and this excess pressure is sent to the nozzle to produce high velocity stream of gases. So what happens is that these gases bounce back and shoot out at the rear of the exhaust, thus producing a thrust propelling the vehicle or the plane. So this 5-module engine, we have the intake, the compressor, the combustion chamber, turbine, and nozzle, is identified as a single spool turbojet engine. So this is a basic principle of a turbojet engine, and if it is a simple arrangement like this, a 5-module, we can identify it as a single spool turbojet engine. Substantial increases in the thrust can be obtained by employing an afterburner or an augmenter, where we, in this afterburner case, where the hot exhaust or the from the turbine, it will be burned again. In this case, there is a second combustion chamber, which normally being positioned between the turbine and the nozzle, and it is quite common in any jet fighter or military aircraft. Moreover, for civil transport, the thrust force may be increased by adding a second spool or a second set of compressor or compressor turbine combination, which we will cover later in our session today. If you look in this particular figure, right, as typical schematic diagram of a single spool turbojet engine, right? So we can see here, this particular figures illustrates two layout for single spool turbojet using either axial compressor. This is an axial compressor, okay? And the other picture B is the centrifugal compressors. The third layout basically is a double spool engine. You can see there are associated with the low pressure turbine and low pressure compressor, high pressure compressor, high pressure turbine, and low pressure turbine before it goes to the nozzle. All right. So the difference between these A and C, basically the number of compressors. In this case, there's only one type of compressor, whereby in the 61C, okay, you have two set of compressor, low pressure compressor and high pressure compressor that is interconnected with the respective high pressure turbine and low pressure turbine. Let us look into the classification of a turbojet engine. We have already touched a little bit when we first introduced this particular course. I believe it is in lecture number 1. In the family of turbojet engine, okay, it can be divided into the first layer, basically whether is it a nuclear type of power source or non-nuclear, right? Whether the engine having afterburner or non-afterburner section, whether it is a single spool or a double spool, right? And if we look here for single spool, whether it is covering axial flow compressor or using centrifugal flow compressor or a combination of the two, axial as well as centrifugal compressor. With regards to the centrifugal flow compressor, whether it is a single entry or the double entry. As you can see from this particular chart, there are many type of classification for a turbojet engine based on the power generation after burning, the spool involved, the type of compressor, as well as the entry for centrifugal flow compressor. Other classifications for turbojet engines may be afterburning or non-afterburning. Afterburning or reheat is a method of augmenting, meaning that it can enhance the basic thrust of an engine to improve the aircraft takeoff or climb, and normally being used for military aircraft during combat performance. So the afterburner is another combustion chamber added between the turbine and the nozzle that normally utilize the unburned oxygen in the exhaust gas. Basically, what will happen, the high energy flow of gases that are generated from the combustion chamber, when it comes to the turbine stages, it still has high energy. And what happened is that right after the turbine stage, we introduce another set of combustion where fuel is injected to the area to create another set of combustion. So the increase of the temperature of the exhaust gas definitely increases the velocity of the exhaust gases leaving the nozzle, and therefore increases the engine thrust by additional 40% at takeoff and much larger percentage at high speed once the plane is in motion. The third classification of turbojet engine is based on their number of spool, as being highlighted in figure 6.1. Turbojet may be single or two, sometimes identified as double or dual spool engine. Okay, a single spool turbojet has one shaft connecting the compressor and the turbine mounted at either shaft end, while two spool engine has two concentric shaft as well as two compressor and turbine. There are also multi-spool engine having more than two compressor as well as the turbine setup. The for the double spool type of turbojet engine, the first compressor next to the intake is identified as the low pressure compressor, which is driven by the low pressure turbine. That is normal low pressure compressor connected to the low pressure turbine, and both together with their shaft as denoted as the low pressure spool. With regard to the next set of compressor, the high pressure compressor, normally situated downstream of the low pressure compressor, and this compressor is driven by the high pressure turbine via the shaft. And both are coupled by high pressure shaft, which is concentric with the low pressure shaft, and these constitute the modules of the high pressure spool. And the single spool engine may be further classified based on the type of compressor being used, and the compression section may be composed of either single or double compressor. Moreover, the compressor may be the type of axial or centrifugal. All right. A single axial or centrifugal compressor is seen in some turbojet. In other cases, two compressor assembled in series are also found. Right, this type of compressors may be either having two centrifugal compressor or an axial compressor followed by a centrifugal compressor. Lastly, this classification closes by the type of entry associated with the centrifugal compressor case. Right, for in this case, centrifugal compressors may have either a single or having a double entry if they were assembled in a back-to-back configuration. Right, so that's just a basic overview of the with regard to the turbojet engine. Okay, and we can then go into the milestone. Basically, we want to look at what are the historical background when we talk about turbojet engine, when actually turbojet engine started, and what are the different parameters or types of turbojet engine. So the following tables, there are a few tables here that I'm going to share with you. It is coming from the textbook where it summarizes important milestone along the history of a turbojet engine, both civil and military applications. All right, I'm not going to go through all of the type of engine, the manufacturer, the year. Okay, it started in 1939. All right, and they also highlighted the maximum power produced. Okay, so you can try to go through by yourself for your own interest. 1943 until 1958, different manufacturer and different. If you realize that the maximum power keep on rising, it become more modern engine being developed, and more power can be produced, right? So we can see here 1958 until 1968, and then up till the 1960s until now. And the numbers are actually keep on increasing in terms of the maximum power produced by the engine itself. Okay? Right. We will focus more of our time on the remaining 6.33, which is the thermodynamic cycle analysis of the single spool. Okay, with regard to thermodynamic cycle, single spool turbojet, which is composed 5 modules: intake, compressor, combustion chamber, turbine, and nozzle. And afterburning turbojet incorporates the 6 module, namely afterburner, and then intake, combustion chamber, and afterburner if it is included in the case, and nozzle are stationary element. Right? There's no moving parts, whereas compressor and the turbine are the rotating element. These are sometimes known as the turbo machinery components. Generally, in aero engine as well as gas turbine engine, there are two types of compressors and two types of turbine being found, right? So these are centrifugal and axial flow compressor, right? So with regard to the compressor, it is either centrifugal or axial. With regard to the turbine, either radial type of turbine or the axial type of turbine. Okay. In the case of centrifugal compressor, which was first used in the engine by von Ohain and Whittle way back in 1930s. Okay. So the axial flow type has several stages of alternate rotating and stationary airfoil blades, okay, which can achieve a compression ratio in excess of 40 to 1. Okay, so basically in compressor, there are rotors that are being attached to the compressor. Okay, we have rotors and stator blades. Okay, and normally it can go for up to 40 or more ratio to 1. Axial turbine consists of one or more stages of alternate stationary and rotating airfoil section blades. So basically, if you look at the turbine stages for turbine component, for axial turbine, you will have also stationary and rotating airfoil blades. And the turbine extract energy, that's the function of the turbine, from the hot exhaust gases to drive the compressor. Okay, so from heat energy convert into mechanical energy, right? Radial turbine are found in small gas turbine like the auxiliary power unit, APU. Okay, so with regard to the characteristics of the engine that must be known in advance, including the flight speed, okay, the speed of the aircraft, okay, or the Mach number. We also need to know the altitude and what is the height of the aircraft flying, and then we need to know the compressor pressure ratio, the turbine inlet temperature TIT, and maximum temperature of the cycle. Okay, so if the burner is operative, we need to also know maximum temperature of the cycle and type of nozzle, convergent or convergent divergent nozzle, okay, and fuel lowest heating value, okay, the Q value, percentage of the blade air, as well as the power delivered to drive accessories, and any aircraft system must also be specified. Component efficiencies for all modules, okay, and pressure drop in stationary modules such as in inlet, combustor, and afterburner must also be known. So normally in the problem solution, you will be provided with the component efficiencies in order for you to obtain the thrust from the engine. When the cycle is assumed ideal, then all efficiencies are assumed unity. We can say that for ideal case, the efficiencies for all component can be 100%, and all the pressure drops are assumed to be 0, like a perfect kind of turbojet. We will see figure 6.3, which illustrate a layout with designation point, figure 6.3a, as well as thermodynamic cycle TS diagram for single spool turbojet with inoperative afterburner, without afterburner, figure 6.3b, and with afterburner, figure 6.3. Okay, so This is the schematic of single spool turbojet engine, showing the type of intake. As you can see here, this is not an ordinary type of turbojet engine. Okay, so you can see that the by looking at the type of intake or the inlet, the aircraft is flying at a very high speed. Okay, and that's why we can see the dotted line there and the shock wave that being generated based on the design. Okay, and then it is followed by the compressor stages. Okay, from 2 to 3, combustion chamber, CC is the combustion chamber, turbine over there, 4 to 5, afterburner where there are fuel being injected to this area before combustion occurs again, second time, and it goes to the nozzle. Okay, so we have convergent, divergent type of nozzle arrangement for this particular example. So with regard to the TX diagram with afterburner, it is being shown here. This is without afterburner. Okay, from 1 to 2, 3, 4, 5, 6, and 7. Okay, and the other one is with the afterburner. This is without the afterburner, and this one is with the afterburner. You can see that the temperature which has already rises in the combustion chamber as it goes to the turbine stage. Then there is another step of temperature when the fuel being injected again. So there's a afterburner process over here. So let us go through the cycle. The cycle, different processes are described here. Okay, where you have -1, the air flow from far upstream approaching to the inlet where the velocity of the air relative to the engine is basically the flight velocity up to the intake, which is usually with some deceleration during cruise and airflow acceleration during takeoff. And the process is always ideal where H, the enthalpy at 0A equal to at 0, 1 position. Okay, what happened next? From 1 to 2, from the inlet to the compressor, airflow through the inlet and ducting system up to the compressor inlet. So since this element is always considered as a diffuser, the air velocity will be decreased, right? And then moving to 2 to 3, where the air is being compressed in the compressor segment, right? And 3 to 4, combustion chamber took place. Air is heated by mixing and burning of fuel. Okay, wrong spelling over there. It is burning of fuel. And from 4 to 5, from combustion chamber to the turbine, product of combustion chamber are expanded through turbine to obtain power to drive the compressor. And 5 to 6, where we have the afterburner, gases may or may not be further heated if the afterburner is operative or inoperative. And finally, 6 to 7, gases are accelerated and exhausted through the exhaust nozzle. All right. So if the engine is not fitted with afterburner, then after state number 5 and number 6, state number 5 and number 6 are coincident, right? It's the same, having the same set of parameters. And the amount of mass flow is usually set by flow choking in the nozzle throat. And the following remarks may be listed. For example, number 1, all components are irreversible, but they are adiabatic except for the burner. Okay, thus isentropic efficiencies for the component such as intake, compressor, turbine, and nozzle are employed. Second statement here is that the components are irreversible, but they are adiabatic, right? Except at the burner. Okay. Thus, isentropic efficiencies for the intake, compressor, turbine, and nozzle are employed. And friction in the air intake or diffuser reduces the total pressure from its free stream value and increases its entropy S. Okay. So at the intake outlet, the total temperature is higher than the isentropic case, while the total pressure is smaller than the isentropic case, which depends on the intake or diffuser efficiency. And this is zeta D, okay, diffuser efficiency. So depending on the flight number, the flight mark number, the diffuser efficiency can range from 0.7 to 0.9, where we are using specific heat ratio gamma to be 1.4. The next statement is that the compression of the air in the compressor, which increases in terms of the temperature, the pressure, and the entropy due to irreversibilities of this process. So such increase in temperature will depend on the zeta C, which is the compressor efficiency, which ranges from 0.85 to 0.9, while the specific ratio is already, we are using gamma equal to 1.37. It's no longer 1.4. A portion of the compressed air is utilized in the cooling of the turbine blades and supporting bearing through air bleed system. Okay. So not all of the air from the compressor will go to the combustion chamber, some of it being used for cooling purposes. So what happens is that the air mass flow rate in the succeeding module is somewhat smaller than what entering the compressor. The burner itself are not simple heater, and the chemical composition of the working fluid changes during the combustion process. So the larger fuel to air ratio F, the greater is the deviation in the chemical composition of the products of combustion from that of the air. Okay, so losses in the combustion process are encountered due to many factors, including imperfect combustion, physical characteristics of the fuel, as well as thermal losses due to conduction and radiation. So such losses are handled in the burner efficiency, zeta B, okay, where the value of zeta B is between 0.97 to 0.99, whereas the pressure drop due to screen friction and pressure drag in the combustor normally 3 to 6% of the total pressure of the entering air. Okay, so next one, the expansion in turbine, where expansion process happening is nearly adiabatic. However, due to friction, an increase in the entropy is encountered. Moreover, the outlet temperature is higher than that of the isentropic case, and thus the available power from the turbine is less than the isentropic case. Okay, so the expansion process associated with the turbine efficiency zeta T, okay, where zeta T sits in between 0.9 to 0.95, and the specific heat ratio is gamma equal to 1.33. Right? So when you have an afterburner, okay, the afterburner is basically similar to the burner. So this will just added fuel with much greater than the added combustion chamber, right? So it is not really a perfect combustion, because obviously when you have afterburner, you are spraying jet of into the hot plume, hot gases, and combustion occur again, and not 100% of the afterburner or the fuel being burned. You can see here the efficiency of the afterburner is around 0.97 to 0.99. Okay, this is probably due to the imperfect combustion and thermal losses due to conduction and radiation. Okay, total pressure drop ranging between 3 and 6%. Finally, in the nozzle, the expansion process is similar to that in the turbine and influenced by skin friction. So zeta N nozzle is between 0.95 to 0.98. Specific heat ratio at this particular section is already 1.36. So it is here worth mentioning that air or gas velocities within the gas generator is normally ignored. And the velocities at the intake and outlet nozzle are the one that need to be calculated. So the different processes through the engine modules can be described again over here. Right. The first section, during cruise, the static pressure rise from segment A to 1 outside the intake and from 1 to 2 inside the intake. Okay, the air is then decelerated relative to the engine since the velocity at stage 2 is assumed to be 0. And then the deceleration is adiabatic. Then the total or stagnation pressure are at state 0 and 1 are equal and greater than its value at 2. So the stagnation temperature for state A, 1 and 2 are equal and independent from any losses. So you can get the corresponding value of T02, okay, which is equal to this expression. Outside the engine, the total pressure remain constant, and P01 is can be expressed as equation 6.2. The pressure recovery within the inlet may be given, and thus the outlet pressure is obtained from this relationship 6.3a. Alternatively, efficient of the diffuser zeta D of the inlet, okay, is given. The outlet pressure will be given by P002. Let us move into the compressor stage, look into the thermodynamic cycle analysis from state 2 to 3, and irreversible adiabatic compression process takes place, which is associated with the isentropic efficiency of the compressor. We have the new term there, okay, zeta C. Thus, with the known pressure pi C, okay, the pressure and temperature at the outlet of the compressor are evaluated from this relation. P03 from equation 6.4, T03 equation 6.5. Moving into the combustion chamber, in combustion process where fuel is injected in an atomized form. So basically, what happens inside the combustion chamber is not there is a valve pouring jet fuel. It's not like that. It is the fuel itself is already formed into atomized form, evaporated, and then mixed with the air. Okay, it's not like in liquid form where you can pour it and so on. It is at atomized form and evaporated. Okay, so spark plug initiate the combustion process. The mass flow rate of the burn fuel is calculated from this energy balance combustion chamber. So the thermodynamic at the outlet and the combustor inlet of the turbine is determined from metallurgical limits. So what happens is that when the temperature at the combustion chamber or the combustor are very high, okay, the turbine itself, if it is not properly being cool, it can be softened. For example, like titanium alloy have a softening temperature at around 750 to 800 degrees Celsius, whereas the combustion temperature and the flame inside the combustion chamber can go up to 2000 degrees Celsius. All right. So the turbine inlet temperature TIT equal to T04, or normally being called as turbine entry temperature. But I always come across during my study also, we are using this turbine inlet temperature TIT. Okay, so with F equal to m dot F over m dot A, fuel to air ratio is determined from the relationship. This is the relationship for fuel to air ratio, equation 6.6. Okay, the stagnation pressure at the outlet of the combustion chamber at state 4 is less than its value at inlet state 3 because of the fluid friction. It's not perfect. Okay, so the pressure drop is either given as a definitive value or as a percentage. So thus the outlet pressure from the combustion chamber is expressed as follows. For PO4 and the other equation also PO4, it is a two set of equations. Now we go into the turbine. The power consumed in the compressor is supplied by the turbine. If the ratio of the power needed to drive the compressor to the power available in the turbine is lambda, okay, then the energy balance for the compressor turbine shaft is given as this expression, right? Over here, the lambda is of the range of 75 to 85 degrees. This is just an ordinary engine, right? Single spool engine. So 15 to 25% of the turbine power is used in driving accessories, and that's why we introduce another term here, mechanical efficiency zeta m. And normally we put very high efficiency at 98% or more. Okay, and this is the expression with regards to the mechanical efficiency, zeta m component over there. The outlet pressure is calculated considering the adiabatic efficiency of the turbine zeta T, P05 to over P04. You will get inserting the adiabatic efficiency of the turbine, you will get the ratio of PO5 over PO4. So then the turbine and compressor pressure ratios are related, right, by this expression, or in general in terms of pi t. Okay, so it is already being generalized in equation 6.9. From 6.1 equation, you can then get equation 6.9d, the ratio of PO5 over PO4, right? And then when we look at the case of the engine without afterburner, so no work or heat transfer occurs downstream of the turbine station, the stagnation enthalpy remains constant throughout the rest of the engine. However, if there is an afterburner, we have two cases. Either afterburner is operative or afterburner is inoperative. Right. Let us look into the first case, inoperative afterburner. So if the afterburner is inoperative, figure 6.3b, no further fuel is burned and the stagnation total temperature at states 5 and 6 is equal. So T06 equal to T05. Okay. The temperature at this state are the same. With regard to concerning the total pressure, okay, a similar treatment to the combustion chamber can be considered. Thus, based on the value of the pressure drop within the afterburner due to the skin friction and the drag from the flame holders, right? So you can get the value of the P pressure at station 6, which is equal to the PO5 minus the pressure difference at the afterburner. Okay. For the case of operative afterburner, for operative afterburner, which is shown in figure 6.3c, a subscript A is added, okay, where we want to distinguish between the afterburner in operative and the other afterburner in operation, in operative, okay. So that's where we introduce capital A there. So it may be higher than the turbine inlet temperature, okay. The reason for such higher temperature is that the downstream element is the nozzle, which is non-rotating part. Okay, so the walls are subjected to only thermal stresses rather than the combined thermal mechanical stresses as the turbine. So pressure at the outlet of the afterburner will also be less than its value at the inlet and can be calculated using equation 611A and 611B. Right? Conservation of mass and energy, okay, discussed with reference to 6.4. So you can put all the energy balance component equation for the afterburner. So there is an additional fuel quantity, right? So M dot FAB, fuel afterburner added, because of course you are spraying extra fuel. Then conservation of mass within the afterburner can be expressed as this equation, right? So you have the component of the mass flow of the new injection fuel that already being injected. Using conservation of energy yields the following. I'm not having intention to pronounce all of that. So the afterburner fuel to air ratio is calculated from this relationship, right? Looking into the nozzle now, in operative afterburner, it's not in operation. A check for nozzle choking is performed first by calculating the critical pressure, and the critical pressure is obtained from this particular relation. All right. So critical pressure is down here, PC, and the critical pressure is then compared with the ambient pressure. So if it is greater or equal to the ambient pressure, the nozzle is choked. Okay, M7 equal to 1. This means that the P7, which is equal to the critical pressure PC, and the nozzle outlet temperature T7 is then calculated from the normal relationship, equation 615, and the exhaust velocity is then calculated as equation 616. On the other hand, so if the ambient pressure is greater than the critical pressure, then the nozzle is unchoked and the exhaust pressure equal to the ambient pressure, right? So you can see here PA prime over there. Okay, sorry, P7 nozzle equal to the atmospheric pressure, PA. Okay, there's no prime, and this is just a comma. I'm very sorry, right? So and the exhaust gases are determined from the relationship. All right, equation 617A and 617B. For operative afterburner, the expansion process in the nozzle starts from 6A when it has afterburner to state 7. The critical pressure is calculated from this equation. So this is being named as equation 618. We will try to stop right after we finish the this particular part 6.33. So if the nozzle is unchoked, the exhaust pressure will be equal to the ambient and the jet speed will be expressed as 619A. If the nozzle is choked, where the air cannot be further accelerated, the equation is being expressed in 619, B. A general relation for the exhaust speed, whether choke or unchoked, may be obtained from our previous lecture, equation 4 to 5, by replacing PA by P7. So this is being expressed in equation 620. So from the previous processes, one by one, from the intake, the compressor, the combustion chamber, turbine afterburner, and the nozzle, right? So it can be illustrated in this particular block diagram. Okay? I believe that is the best time for us to stop before we continue for the turbojet topic to look into the performance parameters already there, right? So before we had the break, we have already looked into the overview, the milestone of turbojet engine, and the thermodynamic cycle analysis of single spool. Now, we want to continue on the performance parameters of a single spool turbojet engine. Okay, so the two engine parameters that define the performance of engine are specific thrust and the specific fuel consumption. All right. So for the specific thrust, normally specific thrust is expressed by T over the mass flow rate, and that's where we call it as the specific thrust relationship. Okay, and being expressed in equation 6.21, and the TSFC, thrust specific fuel consumption. Okay, so in this case, you can see that this is with afterburner, mass flow rate with fuel, mass flow for the fuel with afterburner, and the mass flow of the fuel over the thrust. You can get the thrust specific fuel consumption, TSFC. So substituting the equation 6.21 from equation 6.21, you can then get elaborated version of the TSFC for inoperative afterburner, afterburner without operation. The same equation 621 and 622 are used, but the afterburner fuel to air ratio, the FAB, okay, is set equal to 0. Okay, when there's afterburner is not being used, this can be set to 0, and this also can be set to 0. Okay, for important definitions, there are a few important definitions with regards to the turbojet engine. The first one is exhaust gas temperature, EGT, where exhaust gas temperature is measured with a thermocouple type pyrometer. By monitoring the EGT, normally the pilot can get an idea of the engine's air-fuel ratio, right? At a stoichiometric fuel-air ratio, the exhaust gas temperature is different than in a lean or rich fuel-air ratio. High temperature, normally above 900 degrees Celsius, can be an indicator of dangerous conditions, and that can lead to a catastrophic engine failure. Okay, the other important definition is engine pressure ratio, the EPR, is the ratio of the turbine discharge to compressor inlet pressure, where EPR is used as an indication of the amount of thrust being developed by the turbine engine. Okay, EPR gauge is used to indicate the power output of the turbojet or turbofan engine, where pressure measurements are recorded by probes installed in the engine inlet and at the exhaust. And once collected, the data is sent to a differential pressure transducer, which is indicated on the flight deck EPR gauge, the engine pressure ratio gauge. The EPR system design automatically compensates for the effect of airspeed as well as the altitude. The next one is bleed. What is bleed air? Bleed air in aircraft engine is a compressed air that can be taken from within the engine. Normally, it is coming from the compressor stages, but before the fuel is injected in the burner. Bleed air has high temperature and high pressure, typically around 200 to 250 degrees Celsius with the pressure of 275 kilopascal. This compressed air is used in aircraft in many different ways. You can use it for de-icing of wing leading edge, pressurizing the cabin, pneumatic actuators, starting the remaining engine, and pressurizing laboratory water storage tank. So there's so many usage of compressed air, which is called as the bleed air. Moreover, it is used in de-icing of engine intake and cooling of the turbine blades. Okay, let us move into the double spool turbojet. The earlier analysis of thermodynamic cycle and the performance parameters for single spool turbojet. For the remaining of our time before we end our session, we will now look into the double spool turbojet. Okay, the two spool or double spool engine normally composed of two compressor coupled with two turbine through two shafts, as shown in figure 6.8a. The double spool engine are designed to fulfill the high thrust requirements for both military as well as the civil aircraft. The first spool is composed of the low pressure compressor LPC located downstream to the intake, and it is coupled and driven by the low pressure turbine. LPC is connected to LPT, low pressure compressor connected to low pressure turbine, located upstream of the nozzle or afterburner if fitted. So this is just a schematic diagram, a cutaway of a turbojet, a simple turbojet engine. Okay, a double spool turbojet engine. You have low pressure compressor connected to the low pressure turbine, and you have high pressure compressor connected to the high pressure turbine, and denoted by the black darker line there. So turbojet with afterburner, the same configuration in front, and you have the flame holders, the afterburner duct, and then the nozzle, adjustable nozzle. Okay. The second spool is composed of the high pressure compressor HPC located downstream of the LPC and upstream of the combustion chamber. So HPC connected to the HPT, right? High pressure compressor connected to the high pressure turbine. So low pressure spool rotates at speed N1, while the high pressure spool rotates at a different speed, higher speed, N2. Also, the two-spool turbojet may be fitted with afterburner, which already being shown in figure 6a, and afterburner is located downstream the low pressure turbine and upstream of the nozzle. And most afterburning turbojet are fitted to military airplane. Only supersonic transport, the Concorde and the Tu-144 are powered afterburning turbojet engine, namely Rolls-Royce Snecma Olympus 593 Mk 6.0 and Kolisov RD3651 engine. Moreover, afterburning turbojet employ variable area intake as well as variable area nozzle. Okay, it may be concluded that the two-spool jet engine may be composed of 7 or 8 modules. These are intake, 2 compressors, combustion chamber, 2 turbine, and a nozzle. For afterburning engine, the 8 modules is the afterburner, and the 8 module is the afterburner. Right, let us look into the thermodynamic cycle analysis of a double spool. In terms of the case of real or non-ideal case will be considered here, as the ideal performance can be considered as a special case where the efficiencies are set equal to unity and no pressure loss. Modules of two spool jet engine were listed earlier, okay, and intake is identical to the case of a single spool turbojet. Thus, equation 6.1, 6.2, and 6.3 are used and no need to be repeated again. Okay. Now the successive elements, the low pressure compressor through nozzle will be examined. Right. For the non-afterburning engine, okay, we look at the low pressure compressor for a known compressor pressure ratio pi C1, okay, for the low pressure compressor ratio, and the isentropic efficiency zeta C1. Then the pressure and temperature at the outlet of the low pressure compressor are given in the following relation. We have PO3 expression and TO3 expression. For high pressure compressor, similarly, both the pressure ratio pi C2, right, the second compressor, right, and so we call it as a pi C2, the pressure ratio for the second compressor, and its isentropic efficiency zeta C2 are known. Okay, thus the pressure and temperature at the outlet of the HPC are given by the following. We can now get PO4 and TO4. With regard to the combustion chamber, the temperature at the end of the combustion process, T05, is generally known. It is a temperature at the maximum temperature in the cycle if the afterburner is inoperative. Similar analysis to single spool turbojet reveals the P05 value. And then the energy balance for the combustion chamber yields the following relation for the fuel to air ratio F. Okay, you can get the F component there with the fuel to air ratio equal to mass flow rate of the fuel over mass flow rate of the incoming air of the aircraft. And then we move to high pressure turbine. The power generated in the high pressure turbine HPT is used in driving the high pressure compressor. HPT connected to the HPC. Okay, and if the ratio of the power needed to drive HPC to the power available from HPT is lambda 1, so the energy balance of the compressor turbine shaft can be written as this expression. Okay, for high pressure turbine, the lambda 1 range is around 75 to 85%. And the zeta M1 mechanical efficiency for high pressure spool normally 99 plus percent and nearly 100%. So thus in terms of temperature difference, okay, you have a temperature difference, you can then get the expression of T06 over T005. Then the pressure ratio of the high pressure turbine and high pressure compressor are related as equation 630, whereby zeta T2 is the isentropic efficiency of the high pressure turbine. Zeta T1. This one is zeta T1, high pressure turbine. Zeta T2 is low pressure turbine. So now we move to low pressure turbine. That's where number 2 comes in. Okay, and power consumed in the LPC is supplied through LPT in expansion, where lambda 2 identifying the ratio of the power needed to drive the compressor to the power available in the turbine. Then the energy balance for the low pressure spool is expressed as this equation. Okay, looking into the range for lambda 2, right, for the low pressure turbine is around 75 to 85%, okay, which is higher than the high pressure turbine. Thus, in terms of temperature differences, okay, T07 to T06, you can get this expression, 631. Then the turbine and compressor pressure ratios are then related, P07 or P06. Okay. And looking into the diffuser part, looking at equation 6.1 back, okay, P07 or P06 can be rearranged to include the diffuser part. And then we move to the jet pipe. It's just a straight pipe coming out from the turbine section before it goes to the nozzle, following the low pressure turbine and preceding the nozzle is associated with a slight pressure drop, okay, while the total temperature remain unchanged. That's why T08 equal to T07, right? And then for the nozzle, first a check for nozzle choking is performed. Thus, the critical pressure is obtained from the relation. So we have P08 over PC, just to check whether the nozzle is in choking position. In the case of the nozzle is unchoked, the outlet pressure equal to the ambient pressure, right? Unchoked condition, right? So, but if it is a choke condition, it is not equal. The pressure is not equal to the ambient pressure. The jet speed can be evaluated, V9 can be obtained from this expression 636A. So in the case of the choke condition, then the outlet temperature T8 is calculated from the relation, right? So T08 over T9, you can get this value. The jet speed is expressed as V9 equal to square root gamma HRT, okay? In the case of afterburning, just now is without afterburning, the same treatment for all the modules upstream to the afterburner is applied here. And now, for operating afterburner, the pressure at the outlet to the afterburner is determined from this equation, P08A. A stand for afterburner, okay, equal to P07 minus delta PAB. All right. The maximum temperature in the cycle is obtained at the end of the combustion process. Okay, so that's where T08A is the Tmax. So the afterburner fuel to air ratio is calculated from the energy balance in the afterburner, which gives fuel to air ratio for afterburner in equation 6.38. In terms of the nozzle, for afterburning case, the very hot gases leaving the afterburner will further expand in the nozzle from the state of 08A at the afterburner to state 9 at the nozzle. And as usual, check for nozzle choking is performed. So we check whether the nozzle is in a choke condition, and if it is not choke condition, we can then get the jet speed, V9AB, that is coming out from the exit of the nozzle. So if the nozzle is choked, then the exhaust gas leave the nozzle with a temperature of T9A, which is calculated from this particular relation. And then finally, the exhaust speed is then calculated from the relation. So you get the exhaust speed for the afterburning engine case. Let us now move into section 638, looking into the performance parameters of a double spool. Okay. By performance parameters, similarly, we will look into the specific thrust, T over mass flow rate A, and then the specific fuel consumption, thrust specific fuel consumption, TSFC. Substituting equation 641, the thrust specific fuel consumption can be expressed in equation 642. In the case of inoperative afterburner, 641 and 642 are used, but the afterburner fuel ratio is set to be 0. Okay, you make sure you put it as 0 for inoperative afterburner. So you get the zeta P in this expression. So the mass and velocity of the gases leaving the nozzle are expressed in general as mass flow rate E exit and VE, the velocity at exit. Okay, so the thermal efficiency is expressed as zeta TH, and the overall efficiency is then be written as zeta O overall equal to propulsive efficiency times the thermal efficiency. Remember that thermal efficiency, you have the component of the Q, QR over there. Okay, before we end our session, the final section for today is the micro turbojet. Okay, in terms of micro turbojet, I personally use micro turbojet to look into the gas turbine performance. We also tested micro turbojet in terms of running it using different blends of biofuel. Okay, so small turbojet engine being used to propel as a propulsive system for cruise missile, target drones, as well as small UAVs, unmanned aerial vehicles. Example like micro turbo, TRI 60, you have TRI 61, 60-2, -3, -5, and so on, which produces a thrust force ranging from 3.5 kilonewton to 5.3 kilonewton. This engine is a single spool having length of 851 millimeter, diameter 348 millimeter, dry weight of 61.2 kilogram. So this is a cutaway of SR30 micro turbojet engine, okay, which has the inlet nozzle over here, and it has a radial compressor, just single stage radial compressor, and going into the flow goes into the combustor, right? Then it will be flowing back into the turbine, turbine stages before it is being passed back to the exhaust nozzle. Okay. Table 6.1 shows some data for micro turbojet engine, right? Different manufacturer, the type of model that being used. We in UPM we have Mamba, a black Mamba type of engine. We also have another type of engine. Okay, two type of small, what we call it as a micro turbojet engine, being used in our lab in UPM. Okay. This particular figure 610 illustrates a Harpoon missile, which is an air-to-surface or submarine launch anti-surface anti-ship missile. It is powered by Teledyne small turbojet engine together with solid propellant booster. So this type of engine being installed inside the Harpoon missile. Okay, so with that, I believe we will leave the turbofan section in next week next week lecture number 11, right, which we will talk on the turbofan, looking into the overview, milestone of turbofan engine, classification. Then we look into forward fan unmixed double spool configuration, forward fan mixed flow engine, and forward fan unmixed 3-spool engine. And with that, thank you for your attention. Right, I believe there's another lecture to go for the topic of turbojet and turbofan. So let me just end my session so that we can come back to the class.